The data I'm going to show you today is basically from a project which I've been working on for about past 2 to 3 years with OGT, and it's really exciting where we have come today and how we can actually bring NGS and arrays together to improve patient care. The second project I'm going to talk about is something that James just mentioned, is working on a clinical interpretation software. But it's something which sort of I've been thinking about for a very long time, and I'm glad it's kind of coming together in a clinical format. So I'll show you the concept behind what we are trying to put together in this software. So just to start with the medical exome array part of my talk, as we all know, we have come a very long way in technology. And essentially what we have seen today is that clinical diagnosis and the clinical know-how is still very important irrespective of what technology we use in our laboratories. And I put an example of DMD gene there because when a child comes, a 3 to 4 year old boy who has a Gover sign, still single gene testing is relevant. There is no need to jump to exome and genome sequencing. And I think this is a very important point because as technology advances, I think this misconception of everything is going to go to genome is probably something which is not true. But then after that starts this diagnostic odyssey, which we keep hearing about throughout different talks, where sequencing panels, exome, and genome. So for a panel, I have used the example of a muscular dystrophy situation. And for exome and genome, intellectual disability definitely makes sense to go to that level of testing when you're trying to find the answer for that child. So essentially what we are trying to say here is that how we are going to choose the right test for the patients. So if we just look at it in a different way, if you have a defined phenotype, an ambiguous phenotype or a no clear phenotype, what is the pathway you can follow in terms of choosing the test? So for the defined phenotype, a single causative gene is suspected. Definitely it makes sense to go after the gene. Or multiple candidate genes, you can start with that. An ambiguous phenotype definitely points towards doing a sequencing gene panel, or no candidate genes are suspected, you can go to exome and exome or genome sequencing. In our case at Emory, we've been calling it medical M-exome, and I'll talk about why we are calling it medical exome, M-exome, and what work we have done towards it. But essentially the bottom line behind whether you're doing a gene panel, an exome, or a genome is knowing what the mutation spectrum of that gene actually is. And here's where the problem comes in. DMD, CFTR are genes which we have known for over 2 decades now. These are well-established genes. The mutation spectrum is quite well known. What is not known is these new genes that are getting reported in the literature. A single gene, a single family, and we truly don't know what the mutation spectrum is. So what you see here is I put some examples here where DMD, the mutation spectrum is well established, that majority are deletions, duplications. And at the other end of the spectrum is CF, where we know majority are point mutations. Some common mutations are also known in these genes. But the newer genes, the most recent 2,000, 3,000 genes, the mutation spectrum is not known. So when you're actually doing clinical testing, how do you attempt to cover the entire mutation spectrum of the gene? Because we know point mutations happen, deletion duplications happen. Another thing which we are not really addressing as we keep talking about NGS is the methylation aspect of some of the disorders. So just if you look at gene panels or an exome and genome sequencing, you're going to confirm the variant calls. I'm going to show you the array CGH for CNV detection, fill in the missing bases. We all know that the technology does not cover all the bases. And then consider all these other assays, which are really important assays because NGS is just a test. It is not a complete test. There are other methods that are important for a variety of different panels that need to be done. So for a short stature, you want to cover Russell Silver, which is a methylation assay. Lynch syndrome, you got the EpCAM deletion duplication, PMS2. And then X-linked intellectual disability or autism, you want to do a Fragile X assay. And these are complementary assays that need to be done with your NGS assay to complete the test. So again, going back to this concept of that we want to make sure that along with NGS, you have done a full spectrum of different assays so that you're delivering a complete test to your physician and the patient. And one thing which I've put in italics here is that I've said that NGS will not detect large deletions and duplications. And I know some of you might be thinking that's not true. There are publications which are talking about detecting deletions and duplications from NGS data. But what essentially has been published, let's just look over it a little bit, is that we know that the detection of CNVs add clinical value, and NGS can assay the entire exome. And the other methods which are used and which have been used for a very long time, such as qPCR, MLPA, are really not scalable. But if you look at these publications which I've cited here, which talk about detecting CNVs from NGS, essentially point out to several limitations of using NGS for CNV detection. That the CNV calls must be confirmed. The CNV detection varies based on coverage, quality, and sequence context. And the larger CNVs, the greater the accuracy of CNV detection. Or looking at it the other way, if the CNV is small, your accuracy goes down. And the paper from Retterer et al., which is from GeneDx, has very nicely shown that below 3 exons, it's really hard for them to make a call, and they are getting a lot of false positives. So the false positive rate is quite bothersome. And I'm going to show you some data now which shows that array data can be extremely reliable in this kind of situations. Again, one more thing which I want to emphasize here is the mutation spectrum is important, but curating the genes to enhance in your exome assay, in your array, is very important. What we have done at Emory is we have done a continuous curation program for the past 3 years. We call it the MGene interface, where all directors and postdoctoral fellows are curating the literature as a new gene gets identified and reported. And we actually gather that evidence and put it into this MGene interface where everyone can look at it. And actually this gene number is not correct. We have gone up to 5,200 genes now. But we are actively curating genes which are not associated with disease as well. And this is also a very important step because we are all excited about when a new gene is identified, it gets reported in the literature. Very few papers are published with negative evidence. A good example of that is a wonderful paper which came from the French group, which showed some genes on the X chromosome which are not associated with disease. There are many, many genes like that, and journals are generally not interested in those kind of papers. And that negative evidence is also very important. So we are doing this continuous curation in our lab, and that's where we launched a medical exome project, where we wanted to curate the gene for its evidence, look at the technical aspects of the gene, GC content, deletions, duplications, point mutations, and develop a technically complete assay, not just an NGS assay, but an assay to detect copy number variation as well. And that's where we started working with OGT to develop a medical exome array. The idea being that about 18,000 genes today are not associated with disease, but we want to do gene discovery, so we wanted to maintain coverage across those genes, but super enrich the coverage for 5,200 genes, which are today known to be associated with disease, but their mutation spectrum is not known. And by that I mean we don't know if copy number variation is a major contributor or not. We wanted to maintain the genomic backbone as with any other cytogenetic array you would run in your lab. And we have been doing these arrays for over 7-8 years now. So we have a subset of probes which we know which perform well. And that's where we came down to 2 to 3 exons per probes per exon. This really also depends on the size of the exon. It's not really a one-on-one correlation. We made sure the flanking intron exon boundaries are covered and then actually released it. So what I'm going to show you is actually how we came to this conclusion about whether the gene is associated with disease or not. So basically we just really went out and got the genes that sort of are out there. And this is how we collected. We collected genes from everywhere, from gene tests, from public databases, OMIM, SGMD, Orphanet. We made a library of all these genes and actually started the curation process. Once we had our gene list of 5,000 odd genes, we actually looked at whether the gene on a different set of exon focus arrays is covered completely or not. And there were 2 types of performance issues. One is that the exon was just not covered in the design, and that happens, depends on the who did the design, how the design was done. And an exon was covered, but the performance was not optimal. So we embarked upon this exercise of making sure that genes associated with disease have complete coverage on the medical exome array to detect copy number variation. And that's where we call it the medical exome array. Again, the idea is that a balanced design, put as many probes as possible, but we have optimized how many probes are needed per exon, and make sure that we don't drop out an exon, which was also an important part of this exercise. So what I'm going to show you is 3 cases which kind of highlight what we hear in this conference and read in the literature, is how the paradigm of how we think about a gene and disease association and expanding the phenotype is changing. But also these 3 cases demonstrate the sensitivity of the array. And by that I mean going down to a single exon deletion across all the 3 cases I'm going to show you. So the first example is completing the diagnosis by doing a deletion duplication analysis. Now in this case, the mutation spectrum, it's a newly described gene. The mutation spectrum was not really known. So this is a case of a 12-year-old male, has myopathy, hypertonia, and a variety of clinical features, and also had a lot of previous testing, which we see in many presentations before this kind of exome and sequencing is attempted. This is a pedigree, and what you see here is a proband here who's a 12-year-old male and was sent to us for sequencing. And exome sequencing found one missense change in the MuSK gene. When we reported this out to the physician was not really excited about it, but we gave them the paper, we told them what the clinical phenotype is reported in the literature, and the physician came back and said, yeah, I think this is worth doing. The next step is to do the medical exome array and see if we can find a copy number variation, because we are talking of an autosomal recessive condition, and we did not have a second change in this gene. So medical exome array was done, and what we found was a single exon deletion of exon 6. And you can see here the actual exon deletion. Again, the variant of unknown significance, obviously we have not changed the classification because there is no functional assay, but the clinician went back to the paper, read the paper, and said this phenotype is actually fitting with this child. So going back to this, we were able to do the testing, and we obviously wanted to show segregation, and we were able to show the segregation. So in this case, we could go to a gene which was newly described and find 2 changes. The second example is an unexpected diagnosis by deletion duplication analysis. This is a 2-month-old male, again a range of features, but I think the important features to point out is dysmorphic facial features, cholestasis, and sparse hair. Again, a range of previous testing had been done on this child, and they ordered exome sequencing. Now, as you all know, when we are doing exome sequencing, you hit upon these changes, which are missense changes, and that struggle begins because we are trying to do the genotype-phenotype match. And we reported changes in these 2 genes. Both genes had a proper coverage, so we didn't drop out an exon by exome sequencing. And both are autosomal recessive conditions, and we did not have a second reportable change in either gene. So we requested the physician to do the medical exome array, and what happened was when we did that, we found a deletion of single exon, exon 6 and NSD1, which you all know causes Sotos syndrome. And this kind of threw us and the physician into kind of we need to go back and look at the phenotype. And actually, when the physician came back, we were able to sort of come down to this diagnosis that it was actually Sotos syndrome, and it was due to a deletion of single exon in the NSD1 gene. The last example I'm going to show you all is addition to the mutation spectrum. And this highlights the point on the slide where I was showing you that the mutation spectrum of many of these new genes is just not known. We are still exploring it as the genes are getting reported in the literature. So this is a case of a 14-year-old female who had retinal detachment, pigmentary retinal changes, and a clinical suspicion of a Stickler syndrome or Wagner syndrome. She had a comprehensive eye disorder sequencing panel of 141 genes, which was performed in our lab. And we had reported 3 variants of unknown significance, and this story continues of the variants of unknown significance and how to deal with them in a clinical laboratory. The physician went on to order the array, and this is what we found. We found a single exon deletion of exon 8 in the VCAN gene. So let's look at the VCAN gene. This gene is sort of reported in the literature, but the typical changes reported for this gene are splice site changes. A single exon deletion or a multiple exon deletion has not been reported. Does not mean it's not there. It was just not reported as a part of the mutation spectrum of this gene itself. So here now we have been able to add to the literature another type of mutation event that can happen in this gene. So essentially what I'm trying to say here is that the exome sequencing followed by array-based copy number variation is highly sensitive. What I tried to show you is single exon deletions, which kind of highlights the sensitivity of these arrays as well. And it very well complements what we are trying to do in a clinical laboratory to achieve a final diagnosis for a child with sort of multiple clinical presentation. Now, the next thing I'm going to go to is the comprehensive interpretation platform. And just to give you a little bit of a background to this is, I have worked as a clinical laboratory director for over 15 years now. And that means, I have seen Sanger sequencing go to NGS, but also looked at different aspects of a clinical laboratory, which is cytogenetics and biochemical genetics. So Emory Genetics Laboratory is a full-service lab. We have all 3 labs, and we all work together. We also develop tests which span across all 3 labs. And by that I mean, just as an example, is autism, where we do the cytogenetics array, which we all know has a detection rate of 14 to 18% reported in the literature. We have an NGS panel, a 64-gene panel, which is done in the molecular lab. We have a copy number variation array for this NGS panel done in the cytogenetics lab. And there is a biochemical assay for SLOS, Smith-Lemli-Opitz, which is also included in this autism panel. So what I'm trying to say here is that NGS is a single test, and we all need a clinical interpretation system which spans across all the faculties of doing clinical testing, and how we can bring this all together in clinical interpretation. What I have seen around is that we have a lot of clinical interpretation programs and softwares available now, but they really focus on NGS, and NGS being the center point of all these programs. So this happened through a grant we got from SBRI. It was granted to OGT and Emory University to work in collaboration to develop a comprehensive interpretation platform. So if you just look at the problem itself, we all talk about this, that NGS is not yet ready for easy clinical interpretation. We want to make it as easy and as fast as possible. A large number of tests sometimes are carried out to determine the diagnosis or the treatment option, but how to maintain that data in one single format, which will also sit within our own LIMS system and is formatted to just slide into our own systems. The data types and the quality of data are of different types. Numerous people and numerous departments can be involved. I'm not talking of pathology here. If you talk of cancer, you're also bringing in pathology. Manual curation is time-consuming, data is held in different locations, and there are proprietary databases which have an added cost when you're doing something like this. So looking at the challenge in a different way is that you want to do something which is useful for clinical diagnostics, but you can also have a clinical research module. And what do I mean by that? I think one of the things which is becoming very clear is that clinical diagnostic labs are now doing discovery as well. That means clinical labs are identifying new genes because so much sequencing is happening in these labs. If a consent is given by the patient, this data can be mined for discovery purposes. So we were looking at developing something which is kind of a data warehouse, which can do clinical diagnostics, but also allow us to do clinical research in a setting where we are not sort of interfering with the HIPAA rules and things like that. So with that in mind, we kind of set ourselves on this mission to come up with a module which is allow us to do clinical research, query the data warehouse or the database, use canned queries, questions, ask the data different types of questions. And in the diagnostic setting, what I really want to achieve is when a case comes in the lab, the testing is done, I bring all the data together and be able to report it in a very efficient manner. So let's just look at a little bit about how this, what kind of data am I actually talking of. Again, as I have sort of, I think I've been saying this again and again, is the NGS data is only one piece of the data when you look at a clinical case. You have other molecular data. You have Sanger, Fragile X, SMA can be done by MLPA. You have the cytogenetics data, and then you can have the biochemical data, which is coming from different formats. You have the amino acids analyzers, you have MALDI-TOF. You want to bring it all together into one common format to view the data and actually report it. So what we started doing is putting a back-end functionality together, and in this case, you want to save the patient info, demographics, test ordered, which enters the data warehouse, and that's where the data gets de-identified. And the patient is consented upfront, at least in the US, for exome sequencing and genome sequencing, patients are consented to opt out. So if they don't want their data to go into research, they can opt out. If they have opted out, then obviously it will not enter the data warehouse and it will not get de-identified. The data will just not be used for the clinical research module, where you can ask a variety of questions. At the user interface level, the user comes in and logs in and has permissions already set up for access. If it is both, then get both the clinical diagnostic and the research module. The idea being that through the clinical diagnostic module, you're going to get the case out. You have all data to look at in one common interface. You're not going looking whether biochemical testing was done or not. How am I going to enter the data? But also look at it in a different way, that if you are doing exome sequencing on an adult who you find 2 mutations in the Pompe gene, GAA, your next trigger is going to be to order biochemical testing for confirmation, and this kind of an interpretation software will let you set that trigger in to send to biochemical testing. You don't have to remember to write it on your clinical report. And then the other way to look at it is to get into the discovery module to do, let's say, gene discovery or ask targeted questions from your data set. We've been looking at various ways to develop this clinical interpretation program, and the idea being from day one, I've been saying that it has to be able to get into any LIMS system, and you should not have to tweak your LIMS system to adapt that software into your system. So we've been looking at it and also trying to get in the somatic and the germline guidelines to make the interpretation calls through this software. So this interpretation software is under development. We are in the last phase of getting it all together. Hopefully by the end of the year, we should be able to release it. Again, going back to this problem where doing discovery from clinical data and bringing it all together is what we are trying to achieve, but also making sure that all aspects of clinical testing are now covered in a single interpretation program, which is using this data warehouse concept to do diagnostics and clinical research at the same time. And that was my last slide. At Emory Genetics, we are a lot of people there, but really we are actually 13 directors, but these are the directors who heavily contribute to these ideas and sort of, improving the array situation and making the arrays are comprehensive with OGT, and then also, giving ideas to develop this clinical interpretation software. So with that, I'll stop. Thank you.
Thank you.